You guys all saw the assignment? Or you did that? It wasn't a whole lot. You just reading a couple magazine articles. You submitted your app to Blackboard. Okay, good. Over there, there's a new homework posted due in a week. So make sure you check that out. We'll go through most of the stuff today that you'll need to do that homework. There, I want to do a real quick intro to the idea of neural nets, which is the artificial intelligence method that we're using here. And then I'm going to go through the details of really introducing you to neural nets. You're not expected to know what they are before today. So we'll spend probably 3 weeks going through that. The syllabus has an outline rather than a day-by-day syllabus. It shows you the topics that we're going to cover. You guys all found the syllabus online, I hope. And the grading policy, we're going to have 2 exams in here, 1 midterm and 1 final. Half your grade is projects and homework. And some of those projects tend to be, more than just a homework. So when they get assigned, sometimes we'll have a week and a half to work on them. Make sure you don't wait till the day before to do them because they typically take longer than that. So get started on them early. Often you'll have questions and we'll talk about it in class, help you get going on the project and understand what you're supposed to do. My office, you guys all know where it is. It's right over there. Office hours, Monday, Wednesday, Friday mornings, and Tuesday, Thursday afternoons. I may adjust, well, I can't really do that because I've got a meeting right before class. If you need to catch me at another time outside those office hours, just let me know and we'll figure something out. Let's see, anything else? No, let's get started. Any questions about the class or how it's going to go? Again, I'm going to Zoom every day so that if for some reason you need to be out in quarantine or wherever, please Zoom in. I do think the in-person experience is better. You probably experienced both, right? So come if you can, if you feel comfortable. I will always be here to lecture. So the artificial intelligence that we're using is called an artificial neural net. And it's based on, it's a network of artificial neurons. So first, I'll show you what an artificial neuron is. And then we'll talk about how to connect them up into some simple networks. The key feature of these things is not only do they do calculations as a network, but they're loosely based on your brain, how a neuron in your brain works, and they can learn. So that's the key feature, is you can adjust the network so that it learns data, learns information. And in this class, that's the key feature that we're going to do, is that we want to create a controller that can learn. In other words, if we have a system that you want to be able to control, that is, make it do something, you need to feed it the inputs that get it to do what you want it to do, right? So the artificial neural net learns to do that. It learns to give the inputs to the system to get the output that you want, which is what control is all about. So the first thing I'm going to do is draw a biological neuron. And this is a very simple model. And then I'll show you how an artificial neuron is based on this kind of picture. So we'll do the bio over here and the artificial neuron here. So the biological neuron has a cell body draw a wiggly cell body. And then we're going to have some devices that I'm going to define here in a minute. So this thing in the middle is called the cell body, so that's a neuron. And this neuron takes inputs coming in from these branches. I'm not going to draw them all because there's usually millions of them. And these signals come in through things called dendrites. And so there's signals coming in here, 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 through all of these branches. And then there's a calculation being done in here, and then you get an output out of this thing through what's called an axon. And out here, if we drew another axon coming from another cell body over here, there's a connection between this neuron and this neuron through what's called a synapse. You've heard of synapses in your brain. That's the communication structure that goes from one neuron to another neuron. And what happens is that the signal comes out of this neuron. There's chemical neurotransmitters. You've heard of neurotransmitters in your brain. So there's chemicals that are emitted based on the strength of the signal coming along this way. They go over and then they hit receptor sites on this side. And then they create, based on what gets received over here, they create a signal then that goes in here. And there's signals coming in from all of the other neurons into the cell. And the cell does some real simple processing on that signal and then sends it out that way. And then this thing can be connected by another synaptic gap to another neuron, or a bunch of other neurons going that way. And although this is a pretty complicated process, the modeling of what goes on in your brain as far as the neuron goes is pretty complicated. For an artificial neuron, we could come up with a very simple model of this thing. And so this is an artificial neuron. And you draw a circle that represents the cell body. And in this artificial neuron, we do a summation. And then on the result of that summation, we apply a function. And that gives us an output y. On this side, we have inputs coming in. It's a number x1, a number x2, all the way to xn. There's n inputs. And we multiply those numbers by what are called weights, W. Just double check and make sure this looks clear. It's a pretty nice camera that we got in here. And so how is this modeled after this? Well, you can see that the dendrites are the inputs on this side, and so that's the inputs coming in on the artificial neuron side. And then the synapses are the weights, these multiplicative weights over here. So the inputs are the x's, weights. What else we got? We got the cell body. And the cell body is the summation and the F over here. And then the last thing is the axon over here, that's the output. And that is the output over here. So what makes the neuron, either the artificial or the actual neuron, work and do what you want it to do is what's stored in the synapses and how they interact with the chemicals, or what's stored in the weights here. Because these weights change the signals coming in the same way that the synapses change the signals going across this way. So both of these are simple processing elements. And the power is not in just this one calculation, but when you have 100 artificial or biological neurons or thousands or millions all working at the same time. So both of these systems are massively parallel processing systems. Which means they can do a lot, right? If you had a room full of 10,000 PCs, you got a lot of processing power just in a PC. But if you put 10,000 PCs all working in parallel on a task, you can do a lot. Well, the brain has millions of neurons all working on the task of helping you think and see and all that other stuff. So the idea was build an artificial brain that can learn by adjusting its weights and can do calculations in a massively parallel fashion. So it's really a very high, powerful, high-speed computer. The other thing that controls how the artificial neuron works is what is this thing here? And it's called an activation function, and I'll show you some of the ones that most people use. So the building block of the neural net is the artificial neuron. The building block of your brain is the biological neuron, and here's how this thing is modeled over here after the biological brain. All right, so some activations. This is the F one. A really simple one, linear function. Where you just multiply the input u, value coming into it, by a number. That's just the equation of a straight line. So this thing looks like this. U is the input, f of u is the function. There's another function that's useful, it's called the hard threshold. And this one was originally designed to mimic how the neurons in the brain work. They've discovered that a neuron in your brain receives signals coming in, and it adds them up. That's why I drew the summation here. And once enough signals get brought into the brain, and they're actually chemical ions, it's an electrical ionic signature. Once enough of those collect in the neuron fires. I'm sure you've heard that term, the neuron firing. Neuron fires and sends a signal out. So it needs a certain level of input before it does anything. And so on the artificial side, they modeled this with exactly that. They said, let's make a threshold T. As long as the input U is below that threshold, nothing happens. Like the bio neuron. And then once that threshold is hit, then it jumps up and sends out a 1. So it's a step function, really. And we'll use that in some of the first networks that we create neurons. But then they discovered, well, the biological neuron is not such a sharp threshold. It actually, as the inputs come in, once it exceeds the threshold, it starts to leak current through. And then it pretty rapidly jumps up, but it's not so hard like that. And so they created a soft threshold to mimic how the brain neurons work. So the soft threshold is called a sigmoid. And it looks like this. Let's do 1/2. I missed it a little bit. But it's a soft kind of increase. And the formula for that can be written easily. It's 1/1 plus e to the minus u. And that creates that function. And I didn't even write out the formula for this because it's just if it's less than t, it's 0, if it's greater than t, it's 1. If you look at this, you can see that outputs from this thing are always positive. And so what if we wanted to represent a negative number? Can you guys see over the monitors okay? And if you ever come in here for some reason this desk is up really high and you can't see, please say something. I'll try to put it down as well as possible. Does that help? Okay. Okay, so notice that this is all positive. So somebody said, well, what if we wanted negative numbers coming out? The biological neuron, you can have a negative current. I guess you can, it's going backward, but that doesn't happen. But they said, well, why not in the artificial neuron? Let's expand what we could do to negative numbers coming out. So they created another soft threshold that's called a can H, because it really is, it's the hyperbolic tangent. All right, it's called the tan H. F of u is equal to tan H of u. So that's easy. And if you plot that function, it goes from -1 through 0 up to +1. So it creates another soft threshold, but it can go negative or positive. And there's other ones that people use in the software. There'll be a sinusoidal one and some other choices. But the other one that we tend to use somewhat is what's called a radial basis. And it looks like this. It's an exponential, so you know it's going to decay. When this number in here is 0, it's going to be the biggest possible, right? E to the 0 is 1, and then it's e to the minus, so it's going to tail off. So this creates actually what's called a bump function. Centered at A, and it looks like this. And the neurons in the brain don't behave like that, but psychologists have discovered that there's regions of the brain that will respond to certain inputs. So like when you look at a chair, there's a region in your brain that responds to the image of a chair. Table, a different region. And I said, well, let's create a function so that this function responds to a narrow region of inputs that kind of mimics what the brain does in a bigger structure. Well, as engineers, it's fun to use this as a learning algorithm or a learning tool to try to learn to model and calculate things. So it's a calculator or a computer. But in this class, we want to use this for controlling. So how do we do that? It's basketball season. So let's examine a system that's a ball in flight. In other words, we want to launch a ball, hopefully toward the basketball goal and get it to go through, right? So here's a ball. The physics is the ball being sent off with an initial velocity in a certain direction. And then it goes through the air, gravity acts, and then it comes down somewhere else, right? So the ball will then go and it will go somewhere where it lands. So how do we get that to do that? We have to impart an initial velocity vector to the ball. Well, we could back that up and say, okay, you have to push on it with a certain force, but then when it's let go, it has some initial velocity, right? So we need something out here, the controller, that's going to figure out what kind of initial velocity to put to the ball so that it lands, say, in the basket. Right? So you know where the basket is. The controller is going to figure out what initial velocity to give the ball so that it lands where we want. For the controller, we can have a computer algorithm that does all kinds of calculations. It can be hooked up to a camera. The vision system will detect where the basket is, create a number here, and then go through all kinds of physics to figure out what kind of velocity we need to get that, right? But if we're a basketball player, we want to do that at all kinds of different locations on the court, right? And maybe with a defender's hand up, or you're moving to the right or the left, or maybe there's air currents, right? So how do you do that? We want to create not a person to do this, but we want a robot to figure out how to do this. And how does the robot do this? It either has this computer algorithm inside that figures all that out, or we can put an artificial neural net. A neural net could do that, right? It can take numbers coming in to the neurons, and through a whole bunch of neurons connected together, it could then calculate the velocity that we need. And then the real key feature is we could have it learn to do this. We don't have to program it to do this. We simply send it out there and it starts shooting baskets, and we record where they land. And then we take that data and feed it back into a learning algorithm where it improves its ability to shoot the basket, much like a person does. So part of what we'll be doing is, well, most of what we'll be doing is what's going on in here. Is if you have a system, how do we use this artificial intelligence that can learn to make a system do what we want it to do to control it? Now, when you take, a lot of you guys are in 607 now? Last semester? Oh, you had it, that's right, because it's prereq. In there, you learned how to design a controller to do some simple things, right? You do that in a Laplace domain, and there's lots of tools, lots of successful tools in the Laplace domain to handle simple linear systems. So the tools that we learn in here, if you have a problem and it can be solved with what you did in 607, do that. Because if it's not complicated enough that you have to use a neural net, then it's not a good application for neural nets. It's a good application for traditional control. There are a lot of problems where there's just so much calculation that has to go on in the controller that the computer or the calculations can't keep up with real time. Or the system here is so nonlinear and so complicated that you can't just design a controller to control it right off the bat. And so we want to learn. So the real feature, as we go through, we'll talk about, well, why is this a good application for neural nets? Most often it's because it can learn. And it needs to learn to do the calculations. All right, so I think this is a good time to do the demo. I'm going to give you guys, send some paper around, pass them down that row. Everybody take like 2 or 3 sheets. Make sure everybody got some. Enough over here. If there's extra, you can keep it, or I'll take it back if I scrap it. Got a couple, 2 or 3 sheets. We're going to need this. What I want you to do, take this sheet of paper and wad it up into a paper roll. That's what's next. Exactly this on the paper roll, right? There you have it in the middle. So launch away. It's hard to read it, right? And the back will get 3 or 4 points here on the track. Another try? Yes, please. So we're doing this, and in fact, you guys are using a biological neural net, your brain, to do this. And this is not an easy task. Because your eye has to look at the can, and it has to do vision processing in your brain, and then map what your eyes are seeing through a neural net to the signals that go to your muscle, your arm. So it's going to send the right signals to your arm, and it's going to be a temporal signal, right? So it's going to extend this muscle here, your tricep, and your arm and your wrist, and you're going to let go. It's complicated to get that initial velocity that's hopefully going to hit the can. And then if I set you in here for an hour, you could practice and you would adapt inside your neural network to do this better, right? In fact, the only reason you got even close to the can is because you've had experience in doing this over your life. Because if you took somebody who had never thrown anything before, it would take them a long time to even learn how to throw something. So that's an example of using a neural net to do this kind of control. Now, we got to back out away from that because your brain's pretty complicated to do all that. We're going to do some simple stuff with some simple neural nets. So I'll move this down here and get it out of the way. And we'll clean up after the class. If you want to do it now, I'll take that.
Yeah. Some less for you. Okay, so pipe up everybody. I know, the subbing. No, what? Good for nothing.
How are we doing on time? 1:39, we got plenty of time. While I'm thinking of it, you guys all find the book?
Yes.
We do use it. There's also handouts that I'll put on Blackboard and other resources, but we do use 3 or 4 chapters out of this in this homework. Yeah.
Would you like us to have a hard copy, like if we're going to use it on exams or anything?
No, not in this class. In one of my other classes, I do give open book exams, but in this class, no. So, but electronic copy is fine. It's cheaper. How much is it? I'm just curious. Does everybody buy a hard copy?
It's about $30.
It's an older textbook, so I think you can find used ones.
You have to free person.
How much is it online, or you guys willing to pay?
I got mine for free.
Okay. Let's see. So we're going to look at some simple networks. So we're going to do what are called logic functions. And these are 2 input logic functions. There's 2 values going in, 1 coming out. And the first one we're going to do, so here's input 1, input 2 is the for function. Now, these are binary logic gates, so a 0, 0 going in gives a 0. A 0, 1 gives a 1 because it's either or, this is either 1 or that one's 1. So it's called the or function. And you can even have both of them 1. You get a 1 out because it's or. So either I1 or I2 or both or 1, then we get a 1 out. So I'm going to show you a simple neural net that can do that. It's not rocket science because this is such an easy calculation, but it's going to illustrate how a neural net works. This is neuron 1, neuron 2. The inputs to each of those neurons are the inputs to the logic gate. And these are going to be linear. And in fact, the slope is going to be 1. So really what comes in goes out. So the only purpose of these 2 is to send the output along a branch like that. So the output comes out of here, and it's going to go along a branch to neuron number 3. And then neuron number 3 is going to be a threshold. And the threshold is going to be 0.5. And what we're doing is really describing what's called the architecture of the neural network. We have to tell what each neuron is and what it does, and then we have to tell it how they're connected. So the next information is we need to know the weight here. It's going to be +1. We need to know the weight here. It's going to be +1. And it's time to start keeping track of what's what and naming it so that we know what's where and what it's doing. So we're going to call the output from the neuron X, and the subscript is going to be the neuron number. And we're going to call the sum input coming in U. So U3 is going to be the sum of the stuff coming into it. And down here, U1 and U2 or just I? Because that's the only thing coming in, there is no sum. That's what we're going to call it. So U is a net input. Which means the sum of all the stuff coming in. And then an X is F of U, it's the output. So that matches our picture. I said there's a summation and then an F, right? So the net input is the sum of everything coming in, and then we apply the activation function to get X. And then we're going to name the weights so that we can keep track of where the weight comes from and going to. So W31 goes from 1 to 3. And W32 goes from neuron 2 to 3. So in general, so you think of it as going this direction, coming from right to left, and the first subscript is where it's coming from, and the second one is where it's going to. So example, W31 is from 1 to 3. Warning, different books, different papers will switch that. Some of them have this convention, some of them switch it around, and Wij is from I to J. When I'm doing on the board, I always stick with this convention, but just be careful when you're reading different textbooks that they will switch that sometimes. All right, so what I want to do is calculate this network. And it's called forward propagation because we go from the inputs and calculate the outputs. And you'll see why when we talk about back propagation, that's going the other direction. So I need some space, so I'll let you copy down that stuff on the right, and then I'm going to erase. Everybody good? I'm going to create a table where we calculate all this stuff. And we just work our way from the bottom up to the top. So we're going to list, we're going to calculate U1, and that's going to be easy because it's just I1. And then U2 is I2. And then we're going to calculate U3. And we're going to calculate X3. Yeah, and that's it. Oh, and I do want to add another column here. Let's scoot this over. Sorry about that. U2 is I2. I want to add in what's the target. In other words, what's the correct answer? So if I put in a 0 and a 0, if I put a 0 in here, U1 is equal to that, so it's just 0. Oh, I forgot to calculate. I need to add some more. I'm botching this up. Okay. We're going to calculate X1, X2, then we're going to calculate U3, and then we're going to calculate X3. So if we put in a 0 and 0, what do we want? What's the correct answer over there? 0 for the OR gate, right? So let's see if we get that. So X1 is going to be, because those are linear neurons, X1 is just U1. Linear neuron slope 1, that just multiplies by a slope of 1, and so I get a 0 there. How about X2? X2 is just equal to U2, which is equal to I2, so that's a 0. And now we have this being a 0, and this being a 0. So now we have to take 0 times 1 plus 0 times 1. Not hard, right? So we're going to calculate U3, so 0 times 1 plus 0 times 1 is 0. And now we're going to run it through the threshold activation function. The net input is 0. It's below the threshold of 0.5. Remember, this thing looks like this. So here's 0.5. It's 0 until you hit 0.5, then it jumps up to 1. So 0 net input through that threshold gives me a 0. Is it correct? Yeah, we're going to go back and look at the target. Now, when we start talking about learning algorithms, we'll look at the difference between what we got and the target. And if there's an error, then we're going to adjust things. But right now, we're just doing the forward calculation. No learning. Okay, so let's stick in a 0 and a 1. Oh, by the way, we should put this in here. So this is less than 0.5. So what's the target? The correct answer is we want a 1 coming out. What's x1? 0, because we got 0 going into that neuron, it comes right back out. How about x2? Give me a 1. So now we're going to calculate our sum. Let's say we still got 0 times 1 plus 1 times 1. I get a 1 coming out, don't I? Or sorry, a 1 going in, and that's bigger than the threshold, so that neuron fires, and I get a 1 coming out. And that's all there is to calculating the output of a neural net. Is you start at the bottom, and you just work your way up, calculating all the neurons, net inputs, applying the activation, net output, multiply by the weights, keep working your way up. That's why I started with this simple one, because you can look at it and not even think hard, right? So here we got a 1 going in and a 0. What do we want? The target is a 1. X1 is going to be the same as the input. Same thing here. So now we've got a 1 times a 1 plus a 0 times a 1. We get a 1. It's bigger than the threshold. So that output neuron fires and we get a 1. And you can do this in your head now, right? X1 is 1, X2 is 1. We get 1 times 1 plus 1 times 1 equals 2. It's still bigger than that threshold, so it fires. And then we would say that this works. Why? Because we get the correct answer for each of the inputs. So if one of these gave the wrong output, then we'd say it didn't work because we're getting the wrong answer for one of these. Okay, so there's another logic function that's called the XOR. Called the exclusive OR. And it's so exclusive, this is such a private exclusive club, that you only get a 1 out if you just have a 0, 1 or a 1, 0. But if 2 people try to get into the club, then you get a 0. Nobody gets it. I just made that up. It's an exclusive club. So it's the exclusive OR. Does that network do it? It's obviously not, because the 1, 1 going in is going to give a 1. So can we change the weights or change something in this structure to get that? What do you think? Do we change our program, change our network? Well, we could boost the threshold up, right? But we could boost it up and that would kill off the 1, 1 here, but it's not going to kill off that one because the threshold is not going to do that. We change the weights, make the weights smaller. All that's going to do is maybe make these not fire, but that one's still going to fire. Well, it turns out that with this type of a network, you can't do this function. And some terminology that we need to start talking about. is that this is the input layer. Notice it's a layer of neurons. Well, although we only have one, this is what's called the output layer. Because it gives the output that we're going to look at. And it turns out that a single layer network, the input you don't have, a single output layer network can't do this. So we have to add another layer in the middle to do some calculations that's going to kill off the one that wants to come out of this thing. And that's going to be adding what's called a hidden layer. Hidden because it doesn't see the inputs, it doesn't see the outputs, it's hidden inside. This is what's called. All right, so let me draw that network. So we're going to do an XOR. So I claim, my hypothesis is that this thing is going to do the trick. So this is going to be a neuron, we're going to have a hidden neuron. We still need to have our two inputs because that's the function that we're trying to do. This is our connection, so this is the connective architecture. This is neuron number 1. Number 2, we'll call this one number 3. We could call them anything we want. It's just easy, I think, to number them from the bottom to the top. So here we're going to be calculating x1 equal I1, and we'll actually just skip that step. We'll just list it. X1 is going to be I2. We need to be able to calculate U3. X3, and then U4, and X4. And I still need to tell you what the neurons are. These are linear. Slope of 1, so they just pass through. This is a threshold. Threshold here is 1.5. So the input has to exceed 1.5, and this is a threshold of 0.5. And I still need to tell you what the weights are. W41, because it goes from 1 to 4, is a +1. W42 is a +1. And W43 is a -2. And then these down here, W31 is 1, W32 is 1. And by the architecture, that means that now we know everything that we need to know to calculate the output. We know what the activations are, we know the connectivity, and we're good. So let's calculate this thing and see what happens. And again, we're going to shortcut. We don't need to calculate x1 and x2 because we know that they're just equal to I1 and I2. I was just taking up space here. So in fact, we can list that here. X1 equals U1, X2 equals U2. And our target now is changing because we want a 0 here. Same set of inputs for the XOR. So let's calculate this. We're going to need to calculate U3, X3, U4, and X4. Okay, let's start with the first one, the 0, 0 input. 0 goes in here, 0 goes in here, 0 comes out. We end up with 0 coming out times 1, plus 0 coming out times 1, with 0. Everybody follow that? All right, the signals go up, they just pass through, then we multiply by the weights to get U3. Check, everybody good? Please stop me if I get ahead or talk to it too fast. All right, so the threshold for that thing is 1.5. Fire, no. Go, no go. No fire, right? Less than 1.5, so the output is 0. How about 4? Okay, if I play U4, x3 is 0 times minus 2, plus 0 times plus 1, plus a 0 coming out of here times plus 1. Did I follow this? Zeros, zeros everywhere. So this is going to be 0 and it's less than the threshold. So I get a 0 out and I go like, yay, I got a 0. Like 1 gold coin. How about the 0, 1? Got a 0 coming out here, 1 coming out here, so I'll write it in just so you can track. U3. Got 0 times 1 plus 1 times 1 is 1, right? Still doesn't beat the threshold, so U3, x3 is 0, even though U3 was 1. Okay, how about U4? Remember now x3 is 0, so 0 times minus 2 is 0. 0 times 1, 0. 1 times 1 is 1. So I get a 0 plus a 0 plus a 1. Now that's bigger than the threshold, so that neuron fires. I think you can see that since it's symmetrical, that we flip the zeros and the ones, it's going to be the same story, right? We put in the 1, 0. We get 1 times 1 plus 0 times 1 is 1. Doesn't fire. Is the 1 times 1 plus zeros everywhere else, beats the threshold, and then fires. So far, it's kind of not so exciting. The middle neuron hasn't done anything. Probably a good thing, because if that thing had fired, we'd get a minus 2 going into this sum up here, and then canceling out some of the other stuff. And in fact, that's the magic of that neuron, is that for this last set, the 1, 1 coming in, you get 1 times 1 plus 1 times 1 is 2 for the middle neuron, the hidden neuron. Threshold is beat, so that thing fires. And you see, I think you can see ahead what's going to happen, right? This fires, we get 1 times minus 2. Plus 1 times 1 plus 1 times 1, so the 2's from these cancel out with the minus 2 coming from this neuron, and this thing actually shuts off the whole output so that we do get a 0 for the output for that neuron. I'm just crossing this out is not appropriate because it fired. It's the deal that this shuts off the signals from these two in here, so we get a 0 and neuron 4 runner. So some terminology that people talk about with regard to your brain and neural nets is that these connections excite, they're excitatory connections before, and this negative number inhibits the firing of this neuron. And that happens to your brain. Some neurons are excitatory neurons, some are inhibitory. And so they combine together to give these complicated calculations and thoughts that you can have. I guess inhibitory neurons in your brain keep you from jumping off a cliff unless you really convince yourself you ought to. Like if you're bungee jumping.
Is the way you set it up like with the positive or negative on the inside, does that matter how you set that up? If you would to switch the like positive and negatives?
Like what?
With it, like, so
Could you tell me what way?
like could you do it like positive 2 in the middle and then -1, -1? Still work? I was trying to run through my head. I think the thresholds would be the only thing that maybe messed up. I didn't know if there was like a standard way of.
Yeah, I'm wondering
Right,
if we
not-
flip the signs on these as well, it might do the trick. And you brought up an important point is that while I showed you one neural net that would do this, there's obviously other neural nets that can do the same thing, right? And that's what you're looking at.
There's not like a standard way of writing things.
No. And in fact, we could have increased this threshold to like 1.6 or 1.7, right? And we could have changed the weight slightly and it still would have worked.
Yeah.
So the one feature we notice is that there's no unique network. Which, when you talk mathematics, people, when they're looking at solutions of differential equations, there's a lot of time and energy spent showing the existence of a solution, which is important because if you're looking for it and it doesn't exist, that's bad. But they also want to show the uniqueness so that once you find the solution, it's the unique solution to that differential equation. Here, we don't have a unique solution, but the upside is that there's a lot of possible solutions, so all we have to do is find one of them that works really well. And you'll see that when you do some assignments later on, is that different students will come up with different neural nets that will still solve the problem, and that's okay. So there's no unique network, which means there's a lot of solutions. And so just like people, right? Each person individually, each person thinks differently, but yet you can still have a whole bunch of different kind of people learn how to fly airplanes or shoot baskets. All right, so the last thing I want to do today, we'll wrap this up, because I think it takes a while to get your head around this, is that there is a way where you can feed this information into the network and feed the correct answers, and it will learn the weights. In other words, we can start out not with the knowing this thing. I mean, we have to look at it pretty hard to figure out to get it to work, right? But a learning algorithm allows us to say, okay, let's just start with a small number here as a placeholder, a small number here. And if we do the learning right, it will figure out what the numbers need to be in the weights to solve the problem. And that's what a learning algorithm does, is it adjusts the weights to get the right answer. So I'll show you a learning algorithm that works for certain types of networks. And in some of the background magazine articles and introductory chapters, they talk about the history of what's called a perceptron. In the 1950s, people invented neural nets to try to do image processing. That is, if they had a picture of something, they wanted to be able to perceive from the image what the object was that they were looking at. In other words, a picture of a chair would get recognized as a chair, and so on. This is done with a lot of neural nets currently, but it was a long road to get to the point where a computer could do that kind of recognition. As an example of that kind of recognition, like Siri on your phone uses what's called a deep neural net to process that voice signal and figure out what it is you're trying to say. And that took a lot of work to get that. It still didn't work perfectly. But to get that voice recognition to that level took a lot of work and a lot of people developing neural nets. The perceptron was invented in the 50s, and it is a rule to adjust the weights of a neural net by giving it input data and target values and allowing the weights to change slowly until the answer is right. And this is how it's done. Notice when I drew that picture, I said, well, let's just assign some initial weights. So those are the old weights. This rule says, okay, if I have a set of weights in my network, then I use this and I need to tell you what's over here. And I can update my weight so that the next time I do this, I get a better answer. So you keep doing that until you get the right answer. So what's the stuff over here? I need to draw a picture to go along with this. Here's neuron number J, neuron number I. So these are just two neurons in a network. And the weight that goes between them, according to our convention, is Wij. So that connects J to I. And of course, the output of this neuron is Xi. The output of this neuron we call Xj. And so that's what's going on here is that Xj, the value coming out of neuron J, goes here. The value coming out of the upper neuron, Xi, goes here. And then this is the target for that neuron. So in our example over here, we would take the target minus the X coming out, and that gives us an error. So what this says is that we're going to adjust the weights based on the output error. The output error is this whole thing here. Target minus output. And of course, if we got the right answer, the error is 0. If we don't get the right answer, then the weights are going to change based on this calculation. And hopefully the new weight will give us a better answer the next time we try it. And C here is called the learning rate. And you have to set that to get optimal learning. So the way this perceptron learning rule works is you put in the inputs, you calculate the net output, the net input, the net output, and then you compare what you got with what you wanted. That becomes the error. This is the signal going along this path this way. Right, Xj is the value that's propagating along here and gets multiplied by the weight. So that's the signal going along the path of the weight that you're dealing with. And that makes sense because if there's no signal going through here, let's say you have a 0 coming out of here, 0 times W, it doesn't matter what W is, you're going to get 0 no matter what. So this thing is adjusted based on the strength of the connection here. The stronger the connection, the more it's responsible for the error, and the more that you adjust the weight. Learning rate controls how fast it learns. If you set it too small, it won't learn because there's no learning going on. If you set it too big, sometimes it gets confused. Wouldn't it be nice if inside each of our brains we had a knob that we could crank up the learning rate so we can learn this class like that, right? So next time we will take this learning rule and apply it to learn the OR gate that we just did. So we'll start with a network where we don't know what the weight should be, and then we'll let this learning rule figure out what the weight should be to give us the right answer. I think that's all we'll do today. See you on Monday.